Thank you very much. Appreciate that. All right, so brief bio by myself. Currently VP of EDR at CrowdStrike. Used to work at Apple on a lot of iOS and boot time work. Oh, let's not take the GPS out of there. Co-author of Windows Internals, if some of you are familiar with that book, and basically have been reverse engineering Windows since pretty much 1999, 2000, where I worked on a project called ReactOS that some of you might know. For those of you who don't, it is basically a reimplementation of all of Windows from the ground up as an open source GitHub project. So you can basically just go and download stuff that looks like Windows source code but isn't really Windows source code. My interest in Windows security have always been the rootkits a bit. My interests in Windows security have always been about design flaws and persistence and doing sneaky things on a system by abusing parts of the operating system that are not well understood versus the more traditional, exploitation techniques around, heap overflows and ROP and stack and all that. All that stuff is important, but there's a lot of interesting design flaws and a lot of interesting unknown behaviors that operating systems have, which you can then take advantage of for doing interesting things. A lot of these things aren't even considered bugs sometimes, but they're just things out there that might be useful one day. And in fact, this talk is about some of those things specifically as they relate to boot time persistence. So I'll talk a little bit about EFI-based kernel hooks at boot time, and specifically fileless EFI-based kernel hooks, because some of the most, if not all of the current research around this seems to be around hooking stuff on a file system. And come on, it's not 1999 anymore. That seems kind of lame. I'll also talk about an interesting Windows structure called a loader block that pops up here and there, but really not a lot of people necessarily look into what's behind that. And then I'll talk about PatchGuard and how it relates to boot time persistence, which can be an enemy or can actually be a friend if turned against itself. So we'll see how PatchGuard can be a friend. And I'll talk about ACPI as well. ACPI was something that was talked about a long time ago by people like Loic Duflo in the 2000s, but then it kind of got forgotten. And we'll put this back into perspective, especially with some changes in Windows 8 and Windows 10, kind of bringing all this together. And then we'll basically take all of this stuff, EFI, ACPI, PatchGuard, and see if we can build something end-to-end that takes advantage of and that touches upon all the things we'll talk in this presentation. And then if we have time, we'll have some backup topics on VTL1 and hypervisors and something I'm not supposed to talk about. But we'll see if we get there. Now, if you look at Windows today, obviously it's got amazing security technologies and mitigations that are getting really good and really serious. Like Dave Weston's talk, Blue Hat, was really great about talking about all the hardware protections, Hyper-V in combination with HyperGuard, Device Guard, Kernel CFG, HVCI, Project Octagon, and so on and so forth. But a lot of those technologies make assumptions on the correctness of firmware. So of course, you probably know if SMM is broken, it's basically game over. And they make assumptions on pre-boot safety. So if secure boot is broken, it's pretty much game over. Now, there are technologies like Trusted Boot, TXT, System Guard, which are starting to be leveraged by Microsoft, and maybe an RS5 plus pray to the OEM gods will have something that's more robust. But the reality is that today, you can pretty much assume SMM is broken if you really look hard enough into it. You can pretty much assume Secure Boot is broken if you look hard enough at it. So given that, why isn't there more good EFI, bootkit persistent stuff out there, specifically targeting Windows and targeting modern versions of Windows, instead of basically what came out with Windows 8 and it kind of stagnated there? Why is there nothing out there that's actually kind of, bringing up the state of the art? Well, part of that's because it's pretty hard. I mean, firmware attacks are pretty targeted typically, and so there's not necessarily a lot of interest in doing firmware work because if you look at IC nation states, real-life attacks versus academic ideas, they really want to have things that are going to work on more than just, this one Dell laptop with that one Dell firmware or that one HP laptop. Plus, not everything's UEFI yet. Plus, not everything's Windows 8 and above yet, right? So there's still a lot of interesting Windows 7 and BIOS research. This is changing, but I don't know if we've yet hit the kind of breaking point around that. And there's not a lot of public research out there that you can just take and implement into your EFI bootkit. Of course, a lot of places just copy-paste what's out there and they integrate it, but there's not a lot of copy-paste. Then things like PatchGuard actually do a pretty good job at stopping you. PatchGuard, for example, which is Windows' kind of kernel patch protection technology, has a number of mitigations and things that they do to stop you from having boot time persistence, and Microsoft continues to invest in additional things to break that, like a lot of the system guard stuff that will be coming out soon. But again, with raising the bar just a little bit, I think you can still get stuff that in today's computers will probably still affect 90% of the industry. And maybe someone has done that. Maybe there actually is really good boot time persistence out there. We just don't know about it because none of the defenders are looking at it. So as we're going through these techniques in these slides, if you're a blue teamer, maybe go back and make sure that you're looking for all these things. Because I'm just going to be throwing around a bunch of ideas, which I've tried on my machine and I've got something working. Maybe you should be looking for those things, and maybe we're all surprised. Oh yeah, there is boot time persistence. We just didn't realize it. Whoops. Hopefully that's not the case. All right, so there are a bunch of people who are looking into this, who are building mitigations around this at various companies. Important to give reads to them. Of course, we're always standing on the shoulders of other giants when we're giving presentations like this. So one last thing. There's a lot of techniques here which I don't necessarily think should be, published on the internet yet. So those of you who, stay in front with your giant cameras and you just take pictures of every single slide, now it's time to get ready and do that in my face. I truly enjoy flashes nonstop. All right, so let's talk about fileless stuff that we can do. So if you look at most of the state-of-the-art out there, they're basically using EFI to get code execution. Once they get EFI code execution, they then open a handle to the file system, they scan for bootmanager.efi, and then they patch it on disk, and then when it loads, now you've got a patched version. This is so lame that if you submit a binary to Microsoft's EFI signing system, they even have a fuzzer that detects this automatically by seeing if you're importing the file system. Microsoft signs drivers like ASUS's LED driver that arbitrarily writes stuff in memory, and that gets signed. But this won't get signed. Like doing file I/O from an EFI driver won't. That's how, you shouldn't be doing this. I mean, it isn't 1999 anymore. So instead of trying to patch the file on disk, you should really be patching the thing in memory. Of course, how do you, from your EFI boot time component, know where the kernel is? Well, turns out there's actually something in EFI called event notifications. There's a nice little API called create event EX that lets you register for interesting events that you can get a callback to. Now, one of these events is called EFI Event Group Exit Boot Services. And this is called by the Windows bootloader or by any OS bootloader as they're about to boot the operating system. It's basically saying everything to boot the OS is ready, everything's in RAM, I'm ready to go, let's turn off EFI. And this is basically kind of your last chance as an EFI boot component to do anything, and you get notified about this. Now, what's great is that EFI's event processing mechanism is fully in line. So when the Windows bootloader calls exit boot services, you're in EFI. And then when EFI looks over the list of registered event callbacks and calls that a registered event, it's all in line. So if you look at a stack trace, somewhere in that stack trace is the Windows bootloader with, in latest versions, OSL, FWP, kernel setup phase 1, and you're somewhere, 4 frames, 5 frames deep inside of that function. And inside of that function, there's an interesting loader parameter block structure that I'll talk about, which you should be able to find. I mean, it's in one of the CPU registers, and many times that's non-volatile. So if you know the right register, you can get it. But obviously, that's pretty specific. You can just look for it on a stack. I mean, that function, and the function that calls it, and the function that calls it, all have parameters to that, pointers to that loader block. It shouldn't be hard to find. Now, when this event gets called, you're still in basically physical mode. Everything has physical addresses. You would then want to hand off to a runtime component that remains persistent. But EFI runtime components live in virtual address space. So there's a second event called EFI group virtual address change that notifies you when the bootloader has switched to virtual paging mode and is now going to load the kernel. This is basically 50 instructions after the other callback inside of winload.efi. So you actually get the first callback in line with all the physical addresses on the right stack, and then you wait a few microseconds and you get this other event from pretty much the same function, but now everything's in virtual address space, right? So you can do a lot of the conversions now to figure out where is everything going to be in virtual memory without parsing CR3 by hand or doing things like that. And EFI even gives you an API called convert pointer that any interesting physical address you found in the earlier callback, you ask EFI, please tell me where it is in virtual memory now, and EFI gives it to you. So between these two callbacks, you have everything you need in RAM and in virtual memory to basically have some fun with, for example, the loader block. So the first thing I might want to do in my EFI component is touch that structure. Now, what is the loader block? Well, the loader block is basically a key structure that the Windows bootloader uses to pass to the kernel. Because the bootloader does a lot of stuff. It loads the kernel. It loads the registry. It loads the drivers. It loads the hypervisor. It loads the shim database. It loads the API set mapping, the INF errata, the ELAM hive, the page tables, the kernel imports, the boot entropy, the TPM stuff, and so on and so on. It does a whole bunch of things. It is a 1 megabyte binary. It's almost an entire operating system. And it does all that stuff to get the kernel to be ready. So then it needs to tell the kernel about all this stuff that it loaded, where it put it, what the settings for all these things are, and that's what the loader parameter block. It's a structure that includes all of this information. Now, the structure was never officially documented, but as you might know, the NT4 source code leaked a long time ago, then the Windows 2000 source code leaked, and then the Windows 2003 source code leaked on academic websites, and so between those sources, people kind of knew what the loader block looked like. But then in Windows 7, they just put in the symbol files. So there you go. In Windows 7, you can actually see what this structure looks like. And with this structure, we can then patch and modify interesting things there. Now, after Windows 7, they kind of, I guess, realized, whoops, we put that in the symbols, maybe we shouldn't. And after Windows 8, it's no longer there. So basically, we don't know what it looks like anymore. Windows 8, Windows 8.1, Windows 10, it's not there. But thankfully, in the Windows 10 SDK for Threshold 2 and Redstone 1, they did something better than putting it in the symbol files. They accidentally leaked the entire internal header files, part of their MinWin project, which included the entire definition of the loader block, even comments explaining what every field does. Basically, the piece of the source code accidentally made it into the SDK. Then people actually told them, and they leaked it again in the Redstone 1 SDK. Then they got told again, and in the Redstone 2 beta SDK, they actually did it again. So now it's gone, but you have pretty much a much more modern version of that structure to start reverse engineering. And here's a screenshot, for example. I think this was on Windows 8.1 of what this looks like. You've got interesting things there, like the load order list head, the early launch anti-malware driver list head, the address of the kernel stack, the address of the idle thread, the command line for the kernel, where the kernel's booting from, all of the EFI runtime functions are there, and including some interesting things like, for example, if you write an ELAM driver, which is how in Windows you can block boot time malware, one of the things an ELAM driver receives is the SHA hash and the certificate of anything that loaded at boot. But that actually gets computed by the loader, written into a data structure, part of the loader block, and then what the ELAM driver gets, it's whatever SHA hash is in the structure. So obviously, if you're a boot time component that has access to this structure, you can actually change the SHA hash and the certificate and the publisher of what the ELAM driver is actually going to see. Because specifically, an ELAM driver is not supposed to hash things on its own for performance reasons. It's supposed to just accept and trust the hash it gets from the operating system, which comes from this data structure. So obviously, if you can access the loader block, lots of things you can do. You can put the system in debug mode. You can remove any boot driver from the boot driver list, including an ELAM driver. You can edit the shell hash an ELAM driver is going to get. You can modify the EFI runtime services that the HAL is going to use. You can pass registry in memory. You can mess with the kernel stack. You can do this and this and this and this and that. Obviously, go back at that structure, look at it in the symbols or in the header files. Every field here is an interesting field you can mess around with. But that's not all. That structure is actually only a tiny subset of everything the bootloader creates. Turns out there's a loader parameter block extension, which is another structure that's pointed to by the extension field of the loader parameter block. And this has like 100 other fields in it. And again, this was in the Windows 7 symbols, and again, it leaked in the Windows 10 SDKs. So this provides even more interesting areas of things you can mess around with. Lots of fields here. You can patch ACPI tables. You can patch a shim database that's used for drivers. You can create a headless loader block. You can change, boot flags, like is the boot debugger active. You even get a nice field here, boot application persistence data. So you can persist some data thanks to the bootloader. You get stuff for resume from hibernation. You get access to the graphics stack, timestamp, fingerprint data, ACPI data, HAL extensions. You get access to the entire boot entropy, so you can suck up all the boot entropy and much easily guess what a random number might be later or where ASLR things might get located. So it's a cool structure to mess around with. But that isn't really persistence. It is a way to lower the security of the system, to remove things, to prepare the system in a way that's interesting to you. But you're just messing with data and memory. How do you actually get persistence? How do you get code to survive as Windows is booting and after Windows has booted? Well, with EFI, there's actually something called runtime pool, as well as runtime code. And so you can either have drivers that are marked as runtime drivers that EFI will persist for you, and or you can have runtime allocations, which are basically allocations that'll persist for you. And until like EFI 2.6, the idea that a allocation in memory shouldn't be executable was kind of an unknown thing. Like, it was really revolutionary last year when they introduced non-executable memory in EFI, and then everyone's like, oh my God, you can have memory that's not executable. So most firmware, this is starting to change. All the memory allocations are read, write, execute. So if you allocate stuff from the runtime pool, it'll likely be executable unless you have, a more modern, like the Surface Pro. Good job, Microsoft. It actually has correct data versus code pages. Now, these runtime drivers are typically used, for example, for network boot. Because if you're doing network booting, you're actually using the EFI network driver, and then Windows has to boot far enough to switch to its network driver. But by the time it does that switch, EFI needs to have some persistence basically for the network stack to keep on working. Also changing EFI variables, downloading an EFI update, resetting the computer. Those are all EFI runtime functions that Windows calls through the HAL. So there are components of EFI that persist after boot. Now, how does Windows know how to call those persistent components? Well, in the loader parameter block, there is an array of pointers to all of the runtime functions that Windows is going to call, and then how the HAL calls them. Back in Redstone 4, there even now is an API, it's undocumented of course, where you can ask the HAL for what do you think all the runtime functions are. So if you patch the loader block, you can put your own runtime function there, and so when the kernel thinks it's changing a variable, or when the kernel thinks it's rebooting, it's actually calling your EFI runtime code. And you can even get a pointer back to it by asking the HAL where it is. The other nice thing is that EFI runtime memory isn't considered OS memory. So for example, when you take a crash dump or when other things look at memory, many times that memory isn't really in a location that most forensic tools will look at. Again, in Redstone 4, they added a lot more visibility around this, but in earlier versions, in most crash dumps, you might not actually have EFI runtime memory there because the crash dump code dumps OS memory. It doesn't dump MMIO memory. It doesn't dump EFI runtime memory. So now we have a way of having runtime code and runtime data that persists even though Windows is not booting. So like as I mentioned, we can patch the actual code itself if it is read, write, execute, or we can just add our own code and patch the loader parameter block to point to our code instead of the real code. But this is still fairly visible. I mean, if you do these patches and someone now knows to look at the loader parameter block structure, if someone dumps EFI runtime memory, they're going to see that. So another way we may want to get persistence is to actually patch something in NTOS kernel itself in memory and make the kernel call us through an unexpected way. So instead of just patching the structure everybody's going to be looking at, are there other ways that we can get the kernel to basically call us? And so let's look at what we can do about that. Well, that gets actually hard because the kernel actually, thanks to PatchGuard, has a number of checks, a number of validations to see are you actually floating code. So for example, if the thread executes, PatchGuard will every once in a while verify if RSP, if your stack pointer, is actually a real stack pointer. Because when the memory manager allocates the kernel stack, there's some internal undocumented structures that track that as being a real kernel stack. So if you've got like your own stack that you've created for your own thread on the side, PatchGuard actually detects that. Another way you may try to get persistence is to register a callback that will fire very often. So for example, Windows is always creating threads. So if you register with PS set create thread notify routine, every time a thread gets created, your notify routine gets executed. And this could be one way that you get persistence and execution of your persistent code. Well, PatchGuard checks if all of the registered process notifications and thread notifications are actually loaded signed drivers. And there isn't some unknown free-floating code out there that is registering for those notifications. You might register for object manager callbacks. Anytime anybody opens a handle to a process, you can get notified. And again, get execution of your persistent code. Except you can't, PatchGuard also checks for that. But then PatchGuard has some even more interesting checks. For example, in Windows, you can register an NMI callback. So if there is a non-maskable interrupt, your callback can actually execute. Thought, wow, that's really, really specific. At first I wasn't sure, why does PatchGuard protect NMI callbacks? Or the MPX callback. So Intel has this memory protection technology called MPX, and if there's a bound overflow, the callback actually executes. So that's also a very specific check PatchGuard makes. Or if you have a local APIC, if you reprogram the timer interrupt on the local APIC to execute a function, PatchGuard detects that as well. And it turns out that those are actually all ideas I was having as I was trying to get my EFI runtime code to persist. I was like, ooh, maybe when an NMI happens, that can trigger my code. Except now my code is going to get detected by PatchGuard as not being a real signed loaded driver. Or maybe I can program the local APIC so that every second my code can execute, except it'll detect if the local APIC basically fires that interrupt to something that's basically floating code. So pretty much any idea that I was looking at initially through a callback-based mechanism led to PatchGuard actually detecting that. I was like, okay, that's pretty impressive. Those are not things that people have documented in the past as PatchGuard actually doing. And clearly the defenders of Microsoft know that trying to persist through Windows through floating code is something that might be done out there. So okay, are there other ways that we can then get our code to get triggered? Are there ways that we can avoid PatchGuard? Well, the thing is that PatchGuard itself is actually floating code that executes every once in a while. So how does floating code that executes every once in a while detect other floating code that executes every once in a while? So clearly it must have its own kind of persistence mechanism that maybe we can look at. And so before thinking about that, I said, okay, well, let me look at anything in entosKernel.exe, and let's see if there's anything that's kind of pre-initialized, where if I overwrite what's in memory at boot, before the kernel actually executes, the kernel will basically trust that callback. So I had found this linked list called ALPC message log list head. And this linked list was pre-initialized. Now normally when you have a linked list in Windows, which is a list entry structure, that's called myList, you call initialize list head, and you pass in an address to myList, address of here. And that now makes the for link equal to the back link equal to the head. Meaning that if with my boot time persistent component, I would have patched my list in memory, by the time the kernel starts up, it would have overridden my list with fresh values. But you can, if you want to, do this instead. List entry myList equals RTL initialize list. And then I think you just do that. I don't remember by heart. But this basically is a macro that expands into setting the forward link to the back link to the head. Because you don't really need to do this at runtime. You can set it const that flink is equal to backlink is equal to head using C++ const expression or just even a C const. So you do have the option to basically statically initialize the linked list instead of doing it at a runtime, which can be more performant. So I was looking, are there any callbacks, A, that PatchGuard doesn't protect, and that B, are stored, for example, in a linked list like this or in a static pointer that's not pre-initialized to null. The kernel actually does a pretty good job at making sure that even data variables that are always initialized to null, it re-initializes to null, and it does a pretty good job at initializing all the lists dynamically. But this list was actually pre-initialized. And this is a list of callback pointers that whenever an ALPC message flows, your callback executes. Now, ALPC messages are basically Windows' internal IPC mechanism. So basically, as soon as 5 seconds after boot happens, you're guaranteed there's going to be some ALPC message, and your callback would execute. Now, unfortunately, or fortunately, that linked list is only parsed if ALPC message log enabled is set. So first, your boot time component would have to find the offset of ALPC message log enabled, set that to true, and hope the kernel doesn't set it to false at boot, and then wait for someone to set it to true. And then you'd have to add your callback here, and also get the address of that. But as I was looking at this, I realized, well, you know what? They're not exported. So now I have to somehow find these symbols and put a disassembler in my boot time component. That's going to look very, very shady. Plus, in Redstone 3, somehow, these, as I was doing my work and, sending crash dumps to Microsoft as my persistent bootkit was having bugs, this stopped being an initialized list. Now it was initialized at runtime. So I was like, okay, this doesn't work anymore. Go back to the drawing board. I found another candidate, another global variable in the kernel called etwwdf notify routines. And this one's interesting because it actually has a symbol that's part of the Windows Driver Framework private symbols, which Microsoft ships, because the entire Windows Driver Framework is open source on GitHub, and therefore the entire private symbols are available as well. And this global variable is this data structure where there is a DPC notify routine, an interrupt notify routine, and the work item notify routine. So I looked, okay, what normally sets this and what normally calls this? And so turns out that, and you'll see on the next slide, there's an API called WMI query trace information, which is exported. And when you call that exported API, you get the address of this private symbol. So there's an exported API that gives you that private symbol so you don't have to look it up. Now you might think, okay, but you're in EFI, Alex. You're not going to call a kernel API. Well, actually, why not? I mean, if you actually call a get proc address on an in-memory image, and that API doesn't allocate any memory, it doesn't do any kernel-specific things, literally, if all it does is return address of this, you can call that API even though Windows isn't running yet. In fact, you can even call it from user mode and get that symbol. And it turns out that the Windows Driver Framework on GitHub, you can see it calling WMI query trace information to get the address of, well, basically saves it here. And whatever you put in the kernel in that global variable gets sucked into FX library global's perf trace routines. Then once WDF has captured those 3 pointers, it's got some performance functions like FX perf trace DPC where it checks, is there a DPC notify routine? And if there is, it calls it before actually calling the DPC, which is the Windows term for defer procedure call. The function that handles interrupts checks if there is an interrupt notify routine, and if there is, calls that interrupt notify routine. And this has no PatchGuard checks around it. So basically what we now have is a global variable in the kernel that if we can get its address, and there's an API to get its address even from EFI, if we write an interrupt notify routine there, at boot WDF, which is the first driver that loads, captures the pointers you give it, and as soon as there's any interrupt, any DPC, or any work item, calls your callback. And all you need is to execute once, right? Once you execute once, you know Windows is there, and now you can start doing, Windowsy things. Now that you've established kind of your first execution, your beachhead, so to speak. So you can basically establish your beachhead with a technique like this. Take that global variable, put a function, and as soon as the first interrupt happens, boom, you execute. And now Windows is loaded, you're inside Windows' kernel address space, you're no longer in EFI. Now that you've got your beachhead, though, you want to keep running. And you don't want to create a thread. You don't want to keep running every interrupt either, because that's what's getting visible. So what's stage 2, basically? How do you now keep executing in a sneaky way? Well, how does PatchGuard execute in a sneaky way? Lots of ways. But one of these ways actually is not documented anywhere. And I figure let's spoil the fun. Let's look at something in the HAL. And so every clock interrupt in the HAL, the hardware abstraction layer, there's this check for help clock work union. So I guess it's a union of workers. And every once in a while, and there's code above that checks something, there's a help MCA QDPC. That's interesting. And instead of help MCA QDPC, if basically there's an MCA WIMI callback, that gets called with this magic number. Otherwise, if argument 2 is passed in, so there's argument 1, there's argument 2, then it reads the window structure called the KPRCB. Then from the KPRCB, it reads HAL reserved 7. And then it inserts a DPC based on HAL reserved 7. So it actually executes a DPC if there's a DPC in HAL reserved 7. And this is one of the ways that PatchGuard normally executes. Every once in a while, it puts a DPC there to get itself to run. If you put your DPC there, it doesn't mind. It doesn't detect this is PatchGuard's DPC or this is an evil DPC. And basically, your DPC will execute. And a DPC is a deferred procedure call. It's something that's meant to execute in a deferred way in the background of the system every once in a while. And there are no checks to see if a DPC is floating code or not. DPCs are very low latency, and they happen hundreds of times a second. PatchGuard's not going to be in the business of verifying every single DPC 400 times a second. So DPCs can point to floating code minus kernel control flow guard issues, and that works fine. And it turns out that a work union gets hit every 1.2 billion, anyway, every 2 minutes. So every 2 minutes, your DPC will get executed. As long as you put so what's really cool about this is if you look at the code, if there is something here, it resets it to 0. So you've got to basically put yourself back in there, or you can remove yourself. You can have a second beachhead that runs a second time. You get wiped automatically, and then maybe you can use the third beachhead a little bit later on, right? So you can establish either a persistence so you run every 2 minutes, or pick another point to run a little bit later after that. Now, if there's a good defender out there, now they know this, of course, they might look at that field and see if it's populated or not. And they'll see, is the DPC pointing to PatchGuard's floating code, or is it pointing to somebody else's floating code? But I don't have to put a floating DPC there. Because what do DPCs often do? DPCs queue work items. And so there are certain DPCs the system already has, which will look like, let's say, some random DPC. And they'll often take a parameter that's basically, p void some parameter. And then they'll essentially do x q work item some parameter. And a work item is basically yet another way of executing. This one actually executes in context of a thread. And if you can control some parameter, you can take an existing DPC and make sure it gets fed a parameter you control. And there are actually Windows DPCs you can look up statically from EFI that basically when the DPC gets queued or executes, some param is actually NTOS kernel, bang, G underscore, some global. So you can actually patch some global to be a work item that you control, patch PRCB HAL reserved 7 to be some other global DPC, and any defenders looking at this are going to see a legitimate DPC in a field where Windows normally legitimately puts DPCs pointing to a work item that is normally legitimate, but you've patched then one of the fields in there. So you can keep basically abstracting, peeling away the layers of the onion so that where your floating code actually gets triggered from becomes very confusing to someone that's not a Windows internals expert and knows what's a DPC, what's a work item, what is WDF, right? Pretty sure if I had done this, 5 years ago, and most, forensic tools would not have been able to pick up on this. Now, of course, hopefully this gives you a bunch of ideas of, open up your laptop and see is there anything at HAL reserved 7. And, maybe there is. Maybe it's PatchGuard, maybe it isn't. How do you know? So, hopefully this gives you some ideas in terms of what to look like. Now, that's only part of the story. EFI is one way to get persistence, but this can also be combined with good old ACPI. One of the easiest ways to get persistence from ACPI is the Windows binary platform table. Now, if you buy an average laptop today, it might come with absolute software LoJack. And LoJack has a legitimate reason to be a persistent component on your laptop that even if you reinstall Windows, LoJack still runs and calls home and tells you that your laptop's been stolen. LoJack is basically like, find my laptop for Windows. And it works by basically somehow reinstalling itself, even though you wipe the entire hard drive and reinstall a new version of Windows, LoJack still runs. Now, how does LoJack do that? Well, back in the days, they did some extremely nasty things that if you actually like build an EDR product, most of your false positives will be LoJack, because the things it does are just, whole conversation could be about that. Patches files on disk, does weird stuff in memory from the BIOS. So Microsoft really wanted to clean that up because they didn't want, to allow binaries to do nasty things like that to Windows. So they came up with creating an ACPI table. And this ACPI table is called the WBPT. And it was largely unknown. It was documented, but not really well known, until, of course, Lenovo used this. So there was a big kind of 2 years ago spat about Lenovo using this table to basically drop not LoJack, but essentially, Lenovo persistent threat on the computer. So this is something that if you Google for, you'll find more information about. But essentially, it's a table that points to a physical address and a size. The kernel reads that physical address, assumes it's a PE file, and just writes it to disk. So the kernel takes some RAM address that you specify in some ACPI table and drops it in a file called wbp-bin.exe. SMSS then executes it as long as it's signed. So if it's got some authenticate cert that's SHA-1 and it's linked with integrity check, it'll run. So any of the 20 CAs that issue Windows user mode certs, you're okay. It doesn't have to have a driver cert or a WCL cert, just a legitimate authenticate cert, and you're good to go. Now what's good about this from a defender's perspective is that if you're watching, you do see a file called wbp-bin.exe get dropped to disk. When they execute it, they write in the event log that they've executed the platform binary. So if you're watching your event log by default, you'll see this is executed. But what is interesting is that not only do they drop the file and run it, but they actually call an ACPI method called PBS, platform binary status, and they tell if ACPI code that might exist, hey, I ran this binary. So if you actually have persistent ACPI code, and we'll talk about that in a few slides, and you also have a WBPT table, you can get Windows to execute a binary off disk for you and then tell you that it executed your binary. So this is yet another kind of persistent callback you get to tell you, hey, now user mode is good to go, right? So you've got your first callback that there's an interrupt. Then you've got 2 minutes later, it's been 2 minutes. Then you can use this to know that user mode's there. And all these are ways that you can basically, from firmware, from ACPI, be told where we're at. Now, this is very easy to detect. WinBag even has an extension, bang ACPI table, and you'll see if you've got a WBPT in ACPI. And hopefully you don't, unless you're running LoJack on purpose and you know that. So it's very easy actually to insert an ACPI table that's not supposed to be there. Typically ACPI tables live in Flash and they're static. However, EDK2, which is the EFI runtime, has this nice little API, EFI ACPI table, install ACPI table, and you can install at runtime an ACPI table from your EFI persistent component. That's not normally part of the ACPI tables that are there static. So people assume ACPI tables are static, but many times EFI components are actually allowed to add their own additional ACPI tables. So you could use this as a persistence technique as well from your EFI boot time component. But this is very visible. Like I mentioned, it writes a file on disk. It writes in the event log. So if someone knows what they're looking for, they can see you've added this table. They can see the file on disk. So it works okay, but I think we can do better. We can actually try using ACPI itself as a persistence mechanism. And again, Loic Duflo in 2004, 2005, part of when he was doing research in the French community, he talked a lot about these types of attacks, and then people kind of moved on after that. So just a reminder, ACPI has these things called differentiated system descriptor tables and secondary differentiated system descriptor tables, so DSDT and SSDT. These tables have specialized code called ACPI markup language, or AML, which are written in a script language called ASL. So you write some ACPI script language, you run it through ACA compiler, you get AML. The AML gets dropped into this table. So every time on your laptop you change the brightness from the Windows slider to change the brightness, you're actually executing AML. Every time you go and hover over the battery to see how much battery time you have left, you're executing AML. You close your lid, you're executing AML. And potentially a lot more things cause AML code to execute. Now AML is a markup language. It's not actually CPU microcode or anything like that. So your OS has a component, part of the ACPI parser, in Windows' case that's acpi.sys, that executes this AML in ring 0, kind of like a virtual machine. And so the question is, what can you do in AML? Well, in AML, you can pretty much access any I/O port that you want, and you can touch any piece of RAM that you want, which of course won't be the AML doing this. It'll be the OS parser touching the RAM address you're telling it to touch from within your AML code. In fact, in ACPI 5, you can even do GPIO from within ACPI. This is done through what are called op regions. So you define an op region, an operation region, at physical address 0x blah, 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 and then you can do arbitrary reads and writes against this operation region. And then ACPI.sys will execute that. So from an EDR perspective, if the defender is watching the system, they're seeing ACPI.sys memory mapping some physical address and just doing reads and writes in there as part of a virtual machine that's essentially executing ASL. Now, Windows, out of all the operating systems, is the only one that has an ACPI parser that actually makes sure that those I/O ports aren't like the DMA controller I/O port, or the PICS I/O port, or the BIOS control I/O port, and it also checks that op regions don't point to OS RAM. Even the Intel reference ACPI parser doesn't do that, but Windows does, since Windows XP. Plus, if you are actually running this in ring 0 and you have the hypervisor enabled, well, the RAM addresses you're causing ring 0 to write into, because of IOMMU, because of EPT, you won't be able to bypass, you won't be able to attack the hypervisor, you won't be able to attack VTL1 from ACPI code because the ring 0 parser in VTL0 is parsing that code. But still, are there interesting things we could do to actually patch things or do malicious things with op regions? So one issue is that op regions are actually 64-bit in terms of their base address, but the length of an op region is 32-bit. So an op region can be anywhere in 64-bit RAM, but it can't be bigger than 4 gigs. So you have a 64-bit number being added to a 32-bit number. Depending how you add that, that can cause issues. And it turns out that the Windows ACPI parser, and I found this by random luck in Windows 8 or Windows 7, has a bug where, for example, if you define an op region at 0x1000, which typically is not OS RAM, so that's a valid base address, and give it a length of FFFFFFFF, actually it should be FFFF000, whoops. If you add this the wrong way, of course, what do you get? You get 0. And so there's an op region of 0, and it basically doesn't validate it, even though what you've actually created is an op region of basically the entire lower 4 gigs of the address, of the physical address space. So you can define op regions that cover the first 4 gigs of RAM, which usually has OS data, and Windows ACPI parser won't detect that you've actually done that. Now, they silently fixed this in Windows 10. They probably realized it, fuzzed it. Maybe someone used this. Right? There's a lot of interesting fixes that always made me think, well, I figured this out. I'm not a genius. Someone else must have figured it out too. Either Microsoft's red teams did or something out there abused this. So these silent fixes are always kind of interesting. Plus, modern Windows doesn't actually typically load on the first 4 gigs of RAM. They actually try to load farther away because this actually breaks a lot of techniques that rely on 32-bit RAM. But there's something more interesting. Remember, the check is, does the op region point to OS RAM? And EFI runtime pages are not considered OS RAM. And ACPI tables are not considered OS RAM. Therefore, you can actually have an op region that points to wherever the ACPI table actually got loaded. So you can actually have dynamically self-modifying jittable ACPI code by having an op region that points to the physical address where the AML code is. Now, you do have to know or discover or be told where the ACPI table got loaded, but once you know that, the op region can point to ACPI code itself. Or the op region can point to EFI runtime code. If you know where in RAM your persistent EFI runtime code is located, you can, from AML, patch in memory or modify in memory your own EFI runtime code. So basically that opens up some interesting interactions that most people from the research I've seen have not really thought about. Now, the other thing with ACPI is that AML methods can be executed. As I mentioned, every time you hover over the battery, that executes an ACPI method. Every time you close the lid, that executes an ACPI method. But it turns out that in Windows 8, you can actually just execute an ACPI method yourself, a custom method, not relying on the battery status method or on the lid close method, because there's now a global object called ACPI root object. You can basically just call create file ACPI root object, and you get a handle to the ACPI driver, through which you can then send ioctl ACPI eval method EX, which will execute any AML code with any input parameters that you give it. So if you do have something persistent in user space, you can use that persistent user space component to talk to your ACPI method. Then your ACPI method can then talk to or mess around with your UEFI runtime method. What's the ACL on this, by the way? Well, it's not too bad. Everyone has access, including low integrity. We want to make sure low integrity processes can talk to ACPI. That's important. And so this is a fairly broad access check. App container is not in here, so yes, if you're an app container, then I think you're protected. But low integrity, everyone is pretty broad. So there's more to it though, because you can actually even talk from ACPI to the kernel. There's something called an op region handler, and both Linux and Windows support this. I don't know about Mac, but I assume so, because it is part of the standard. And an op region handler, and you can read Microsoft's documentation, but if you just Google for op region handler, allows a ring 0 driver to say, hey, there's any ACPI method out there that references an op region between X and Y, please send me any read and every write that it makes. And then your callback receives the offset, the base address, read or write, and then the data being read or written to. So you can basically trick ACPI into having AML code that's touching RAM, but that address isn't actually going to be anywhere in RAM. It's going to be a magic address you register from your ring 0 driver, and then your ring 0 driver gets every read and every write to give an offset, and the 32-bit payload being written or read from. So that allows you to have a ring 0 to ACPI communication mechanism that's bidirectional. You call an ACPI method. The ACPI method then touches an op region. That op region is actually just a fake magic number to call your callback, and now your callback gets some information. So you can basically build an ACPI ring 0 bidirectional side channel this way. The other thing you can do, which is even more undocumented, in fact, if you search for it, the only thing you'll find is people on OSR Online and other websites asking, how does this work? I'm trying to use this. It's crashing. Called Register for Device Notification. Turns out that ASL has a notify opcode. And then you can put a number there that's supposed to be over 0x80. When the ACPI parser sees that an ACPI method uses notify, it checks internally if any ring 0 driver has registered for notifications from that method. And there is a pseudo-documented way, it's on GitHub now thanks to Microsoft's driver samples, of basically registering for notification and basically saying, hey, anytime any ACPI method does notify 85, please call my callback. So you can also have ACPI methods basically say, and this is delivers an interrupt. So you can have a driver that receives what is essentially IRQ9, interrupt 9, from within your ACPI method. So this you can basically build end-to-end channel between ring 0 and ACPI. How do you then get from ACPI to firmware? Well, let's try putting all this together. All right, so somehow you're executing in UEFI, right? I told you from the beginning, we're going to assume there's some persistent component that somehow got there that bypassed secure boot. Let's wave our hands. That persistent boot time component then registers for the events I told you about. As part of registering for those events, it patches whatever it needs in the kernel, such as the example that I gave you. It also potentially loads any ACPI tables that it wants. Maybe it loads a Windows Platform binary table. Maybe it loads a custom SSDT with custom AML, or maybe just it patches existing AML. Those are all options that you have. Then you allocate some UEFI runtime memory. Then maybe you patch the loader block, maybe weaken the security of the system a bit, maybe enable debugging, maybe disable PatchGuard, or maybe you don't patch anything. Maybe you let your ACPI code be the one that will do the badness. And when you install that ACPI table, you control the AML, and you know where the physical addresses of everything are. So when you actually build the AML, you can dynamically patch your own AML to point to interesting physical addresses, or you can be told about those physical addresses. So you do all that, and by the way, if you actually have read-write executable UEFI pages, to protect the system, if the hypervisor is enabled with device guard, you'll actually execute a VTL1 as well, so even better. You can also use UEFI runtime variables, and you can store anything you want in there as well. Those are a little bit more visible, but you have all of these options. Then in your ACPI component, you can, for example, have a op region that points to interesting RAM that's not OS RAM. Again, pointing back to your AML code itself, or maybe just perhaps pointing to EFI runtime code. So what you could actually do is have an EFI runtime variable that stores an interesting address, have your user mode component call an ACPI method passing that interesting address. Your ACPI method then patches whatever is in RAM with an ARM region, or maybe sends it to a driver. Again, you can combine all of these possible things. Another idea is, can you actually call EFI runtime code from AML? I mean, AML is basically parsed VM code. EFI runtime code is C code. But one of the things you could actually do is you could have, for example, your persistent callback that you know runs every 2 minutes. And it basically could do something like this. Switch G underscore command. And then it could have, case, command 1. And then here it could, call some interesting kernel API or do something interesting. In fact, do something could also get G underscore command data. And every 2 minutes you execute this. Now, if in AML you know the address of G command in RAM and you perhaps persisted it through a variable or persisted it when you installed the AML, and you know the physical address of G command data, you can then essentially in AML have an ACPI method, called foo, that receives param1 and param2 from user space, and can essentially do, using an ob region, the equivalent of star G command equals param1, and of course star G command data equals param2. In fact, you can even make your EFI runtime code call arbitrary binary data that you know is going to be read, write, execute, and make your ACPI method write arbitrary input data into an arbitrary buffer that you know your EFI component is just executing. And since you're executing every 2 minutes you're just checking what queued command should I be doing, and your ACPI method is basically passing that up. And now you have a very nice chain of components, each of them which, the ring 0 component looks like is just running every 2 minutes reading a variable. And if you statically analyze it, all you're going to see is a ring 0 driver, all you're going to see is an EFI runtime piece of code that's checking a variable and calling something. And you're not even going to persistently execute. So you can combine all these things in interesting ideas. Now from user space, again, you might want to have a user space component that either gets dropped through the WBPT, or maybe there's a website that when your victim or target visits, the website, from low-IL, from everyone, executes an ACPI method, or you just know there's certain ACPI methods that execute automatically. But then you have to find some sort of ACPI method that executes automatically where you can control the input parameters. And that might not be so easy. So this now forces you to have like an executable component on disk or something like that, which isn't great. Can we live off the land, as Matt Graber likes to call it? Well, what about WIMI? We all love WIMI, right? Can we get WIMI into this? Of course we can. There's a WIMI ACPI spec, and a lot of motherboards actually use this. With the WIMI ACPI spec, if you write a specific type of ACPI method in AML, and you publish that you support WIMI ACPI in your ACPI table, there now is a way that from WIMI you can execute arbitrary ACPI commands. And of course, WIMI can be called from PowerShell, WIMI can be called from JScript, WIMI can be executed from a VBA macro. So putting this all end-to-end, you can basically have a Office document with a VBA macro that executes some WIMI command, that executes an ACPI method passing some interesting commands. The ACPI method is touching some interesting RAM, where an EFI runtime persistent component is checking it every 2 minutes, and you have a very nice end-to-end chain that most defenders are not going to know how to understand. And if you look at it in pieces, it doesn't make a lot of sense, right? Piece 1 is some VBA that's calling an ACPI method. Piece 2 is an ACPI method that's writing somewhere in RAM. Piece 3 is something in RAM that's executing things. And by piecing it together like this, unless someone has the whole end-to-end chain and knows where to look for each piece, they're not going to be able to find us. So ideas like this, maybe other bad guys are thinking about it, and maybe defenders should be thinking about this too. I'm not the only one who can come up with a boot time persistent chain like this that works on Windows 10 and that bypasses PatchGuard. Are you looking for those places? Did you think that all these places exist? Are you validating your CPI code? Are you validating your EFI runtime code? And so on and so forth. Now, one little last piece is I've mentioned a few times that if you have read, write, execute EFI code, it executes in virtual trust level 1. It executes protected by the hypervisor. And at first I never really understood this. I never bothered to explain it. It turns out that if you have hypervisor code integrity in Windows and you're asking the hypervisor to verify all code pages, if your code pages are writable in EFI, then obviously it can't give you code integrity guarantees. So if your EFI pages are read execute, then EFI code runs in normal VTL 0 because the hypervisor can check if they're code signed and then basically trust that they're not going to be modified anymore. But if your EFI runtime pages are read-write executable, then DeviceGuard can't really give you the guarantees that it needs because then you have read-write executable code. So what it does to actually protect you is it runs that code in VTL 1 knowing that thanks to nested page tables, nobody can actually patch that code. So interestingly, if you have insecure firmware to secure you, that firmware runs in VTL 1, which does mean that if you have boot time persistence, you can actually get boot time persistence in VTL 1, not just in VTL 0, if you have insecure firmware. Now, if you have secure firmware, that doesn't apply, but that's where there's this kind of interesting dichotomy where insecure firmware gets protected by running it in a secure mode, and obviously VTL 1 has certain advantages. All right, so KSR, forget about KSR. There's no such thing about KSR. I'll see you next year. Maybe we'll talk about KSR next year. And basically, I'm done. Thank you.